Welcome to Astro Odyssey. Explore the universe. Imagine a sound so ancient it has been traveling for nearly 13.8 billion years, crossing the vastness of expanding space, drifting through galaxies, sliding past stars, and passing silently through the emptiness between them. It is not a sound we can hear with our ears, but a faint whisper written in light itself, a relic from the earliest moments of existence. A cosmic echo from a time before planets, before stars, before even atoms as we know them. This ancient signal fills the entire universe, bathing every corner of space in a faint glow. And remarkably, we can detect it. Scientists call it the cosmic microwave background, or simply the CMB. It is the oldest light in the universe, a fossil from the Big Bang. And it carries within it the blueprint of everything that would ever exist. To understand the cosmic microwave background, we must travel back to the beginning, back to a time when the universe was not filled with galaxies, but with a searing ocean of energy. The Big Bang was not an explosion in space. It was the sudden expansion of space itself. In the first fraction of a second, the universe was unimaginably hot and dense. Temperatures soared into the trillions of degrees. At such extremes, the concept of matter barely existed. There were no atoms, no protons, no electrons, only a swirling, chaotic soup of fundamental particles and radiation, all interacting constantly in a dense, glowing plasma. In those earliest moments, light could not travel freely. Photons, the particles of light, were trapped in this thick cosmic fog. Every time a photon tried to move forward, it collided with a charged particle, bouncing in a random direction. Imagine trying to see through a dense fog where every step forward causes you to bump into someone. That was the universe's condition for hundreds of thousands of years. It was bright, energetic, and completely opaque. As the universe expanded, it began to cool. Expansion stretches space itself, and as space stretches, the energy within it spreads out. Temperatures dropped slowly but steadily. After about 380,000 years, a mere moment on cosmic timescales, the universe cooled, enough for a dramatic transformation to occur. Electrons and protons, which had previously been too energetic to stay together, finally combined to form neutral hydrogen atoms. This process is known as recombination. With the formation of neutral atoms, the cosmic fog suddenly lifted. Photons no longer bounced endlessly between charged particles. Instead, they could travel freely through space for the first time. The universe, once opaque, became transparent, and the light released at that moment began its long journey across the cosmos. That light is what we now detect as the cosmic microwave background. At the time of its release, this light was extremely hot and energetic. It glowed with a temperature of about 3,000 degrees Celsius, similar to the surface of a star. If you had been there, the universe would have looked like a blinding, glowing fog of orange-white light stretching in every direction. But the universe did not stop expanding. Over billions of years, space stretched further and further, and as it did, it stretched the light traveling through it. Light behaves like a wave, and when a wave stretches, its wavelength increases and its energy decreases. The once blazing radiation from the early universe cooled and shifted into longer wavelengths. Today, that same ancient light has been stretched so much that it is no longer visible to our eyes. It exists in the microwave part of the electromagnetic spectrum, and its temperature has dropped from thousands of degrees to just 2.7 degrees above. Absolute zero. Yet despite this dramatic cooling, the cosmic microwave background still fills the universe uniformly. It is everywhere. If you could tune an old television to a dead channel, the static you see is partly caused by this ancient radiation. Every direction you look in the sky, this faint glow is present. It is the afterglow of creation itself. The discovery of the CMB was one of the most accidental and profound moments in modern science. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey. They were testing a large, horn-shaped antenna designed for satellite communication. But no matter where they pointed it, they kept detecting a persistent background noise. It was faint, but it was everywhere. They tried everything to eliminate it. They checked their instruments, examined the electronics, and even cleaned out pigeon droppings from inside the antenna, jokingly referred to as white dielectric material. But the noise would not go away. What they did not realize at first was that they were listening to the oldest light in the universe. At the same time, a team of physicists at Princeton University had predicted the existence of this cosmic background radiation as evidence of the Big Bang. When the two groups compared notes, the realization was immediate and profound. Penzias and Wilson had discovered the echo of the Big Bang itself. For this accidental but monumental discovery, they were awarded the Nobel Prize in Physics. But detecting the cosmic microwave background was only the beginning. Scientists soon realized that this ancient light was not perfectly uniform. It contained tiny variations in temperature differences of just 1 part in 100,000. These tiny fluctuations might seem insignificant, but they are the seeds of everything we see today. They represent regions where the density of matter in the early universe was slightly higher or lower than average. In the denser regions, gravity had a stronger pull. Over millions and billions of years, these regions attracted more matter, growing into vast clouds of gas. Those clouds eventually collapsed to form the first stars, the first galaxies, and the enormous cosmic structures that fill the universe today. In other words, the tiny ripples in the cosmic microwave background are the fingerprints of the universe's future. They are the earliest evidence of the structure that would eventually become galaxies, clusters, and sectors. To study these subtle variations, scientists launched a series of space missions dedicated to mapping the cosmic microwave background with increasing precision. The first major breakthrough came in 1992 with the COBE satellite, the Cosmic Background Explorer. COBE produced the first detailed map of the CMB, revealing those tiny temperature fluctuations. When the data was released, scientists were astonished. The patterns matched the predictions of the Big Bang theory with remarkable accuracy. Later missions, such as WMAP and the Planck satellite, provided even more detailed maps. These missions measured the temperature differences across the entire sky with extraordinary precision. The resulting maps looked like colorful, speckled, patterned cosmic baby pictures of the universe. Each tiny spot represented a region of slightly different temperature and density in the early universe. From these maps, scientists were able to determine some of the most fundamental properties of the cosmos. They measured the age of the universe about 13.8 billion years. They calculated its composition, about 5% ordinary matter, 27% dark matter, and a mysterious 68% dark energy driving the universe's accelerated expansion. All of this information came from studying faint variations in the oldest light in existence. The cosmic microwave background is more than just a relic. It is a time capsule. When we observe distant galaxies, we see them as they were millions or billions of years ago, because their light takes time to reach us. But the CMB takes us even further back, far beyond the formation of the first stars. It shows us the universe as it was just 380,000 years after the Big Bang, a moment when the cosmos was still in its infancy. In a sense, the CMB is the ultimate baby photo of the universe. It shows a time before galaxies, before planets, before life. A time when the entire cosmos was a hot, glowing sea of particles and radiation, just beginning to cool and organize itself into the structures we see today. And yet, even after decades of study, the cosmic microwave background still holds mysteries. Scientists continue to search for subtle patterns in its light clues about what happened in the first fractions of a second after the Big Bang. Some believe the CMB may contain evidence of cosmic inflation, a period of incredibly rapid expansion that occurred almost instantly after the universe began. Others search for hints of new physics, hidden in the faintest variations of this ancient glow. The universe may be vast and ancient, but the cosmic microwave background reminds us that everything we see, every star, every planet, every galaxy grew from tiny ripples in a sea of light. It is a quiet whisper from the beginning of time, still echoing across the cosmos, waiting for us to listen. When scientists first mapped the cosmic microwave background in detail, what they saw was both subtle and revolutionary. the radiation looked almost perfectly uniform, as if the entire universe had been born in an incredibly smooth, evenly mixed state. But hidden within that smoothness were tiny irregularities, minette. Temperature differences scattered across the sky like faint freckles on an otherwise flawless surface. These variations were incredibly small, measuring only about 1 part in 100,000. If the universe had been the size of Earth, the difference would have been no greater than the height of a small hill. And yet these tiny fluctuations were not just random imperfections. They were the seeds from which all cosmic structure would grow. To understand why these tiny ripples were so important, imagine a perfectly still pond. If the water were completely flat and motionless, nothing would ever happen. But drop a small pebble into the surface, and ripples spread outward. Those ripples create movement, patterns, and change. In the early universe, the temperature fluctuations in the cosmic microwave background acted like those first ripples. They marked places where matter was slightly more concentrated than in surrounding regions. Gravity, the force that pulls matter together, amplified these differences over time. Where there was a slightly higher density, gravity pulled in more matter. As more matter gathered, gravity grew stronger, attracting even more material. Over millions of years, these tiny differences grew into massive clouds of gas. Those clouds collapsed to form the first stars. Groups of stars became the first galaxies. Galaxies gathered into clusters, and clusters formed vast filaments and walls, creating the enormous cosmic web that stretches across the observable universe in this way. The cosmic microwave background is not just a snapshot of the past. It is a blueprint for the future. The patterns seen in the CMB contain the earliest traces of every galaxy, every star, and every planet that would ever exist. But where did those tiny fluctuations come from in the first place? To answer that, scientists had to look even further back in time, far beyond the moment when the cosmic microwave background was released. They had to examine the first fraction of a second after the Big Bang, when the universe was smaller than an atom and expanding at a mind-bending rate, according to modern cosmology. The universe experienced a brief but extraordinary event called cosmic inflation. Inflation is thought to have occurred just a tiny fraction of a second after the Big Bang, perhaps as early as 1/10,000,000,000th of a trillionth of a trillionth of a second. During this unimaginably brief moment, the universe expanded at an exponential rate, growing from subatomic size to something far larger than a galaxy in the blink of an eye. This expansion was not like a typical explosion. It was space itself stretching. Every point in the universe moved away from every other point. It's not because they were traveling through space, but because the space between them was growing. It was as if the very fabric of reality were being pulled outward in all directions simultaneously. Before inflation, the universe was governed by the strange rules of quantum physics. At those tiny scales, the universe was filled with quantum fluctuations, random, microscopic variations in energy. These fluctuations were incredibly small, but inflation stretched them across enormous distances. Tiny quantum ripples became cosmic scale variations in density. When inflation ended, the universe continued expanding at a slower rate, but the fluctuations remained, frozen into the structure of space itself. Hundreds of thousands of years later, when the cosmic microwave background was released, those same fluctuations appeared as tiny temperature differences across the sky. In other words, the patterns we see in the CMB today may be the stretched-out fingerprints of quantum events that happened in the first instant of existence. The largest structures in the universe, the vast clusters of galaxies spanning millions of light-years may have originated from fluctuations smaller than a proton. This idea is one of the most astonishing and awe of science. It suggests that the structure of the entire cosmos may have been shaped by quantum randomness in the earliest moments of time. The universe we see today, the stars, the galaxies, even the atoms in our bodies may ultimately trace their origins to tiny fluctuations in a quantum field billions of years ago. The cosmic microwave background provides one of the strongest Pieces of evidence for this theory: when scientists analyze the patterns in the CMB, they find that the fluctuations match the predictions of inflation with remarkable precision. The size, distribution, and scale of the temperature differences align almost perfectly with the mathematical models describing an inflationary universe. But the CMB does more than confirm inflation. It also acts as a cosmic ruler, allowing scientists to measure the geometry of the universe itself. One of the biggest questions in cosmology has always been, what is the shape of the universe? Is it curved like the surface of a sphere? Is it open and saddle-shaped? Or is it perfectly flat, extending infinitely in all directions? The answer lies in how the temperature fluctuations in the CMB appear to us. Scientists can measure the angular size of the tiny hot and cold spots in the radiation. If the universe were strongly curved, those spots would appear distorted. But observations from satellites like WMAP and Planck showed something remarkable. Spots appeared exactly the size predicted for a flat universe. This does not necessarily mean the universe is infinite, but it does suggest that, on large scales, space is very close to geometrically flat. It behaves according to the rules of Euclidean geometry, the same geometry taught in school. It's where parallel lines never meet, and the angles of a triangle add up to 180 degrees. This discovery was profound. It meant that the overall structure of the universe was not random or chaotic, but governed by precise, measurable properties. And those properties were written into the faint glow of the cosmic microwave background, even more astonishing. The CMB allowed scientists to determine the universe's composition. By studying the exact pattern of fluctuations, how large they are, how frequently they occur, and how they are distributed, cosmologists could infer how much ordinary matter, dark matter, and dark energy exist in the cosmos. The results were surprising. Ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 5% of the universe. The rest is invisible. About 27% is dark matter, mysterious substance that exerts gravitational pull but does not emit or absorb light. And a staggering 68% is dark energy, an unknown form of energy that is causing the expansion of the universe to accelerate. All of this knowledge about the universe's shape, age, and composition came from studying a faint glow left over from the Big Bang. The cosmic microwave background is, in many ways, the ultimate scientific treasure. It is a record of the universe's infancy, preserved across billions of years. It is a map of the primordial fluctuations that shape the cosmos, and it is a tool that allows scientists to test their deepest theories about the origin of everything. Yet, the CMB is not just a scientific curiosity. It is also a profound reminder of our connection to the universe. Every atom in our bodies was once part of that early cosmic plasma. The hydrogen in the water we drink, the carbon in our cells, the oxygen we breathe, all of it traces its origins back to the processes that began in the early universe. The light of the cosmic microwave background has been traveling across space since long before Earth existed. It has crossed galaxies, drifted through interstellar space, and continued onward through the expanding cosmos. And now, after nearly 13.8 billion years, a tiny fraction of that ancient light reaches us, carrying with it the story of the universe's birth. When scientists detect the CMB, they are not just measuring radiation. They are listening to the echo of creation itself, a whisper from the beginning of time still traveling through the cosmos, waiting to be heard. Detecting the cosmic microwave background is not as simple as pointing a telescope at the sky. The light we are trying to observe is incredibly faint, far colder than anything we encounter in everyday life. It is just 2.7 degrees above absolute zero, the coldest temperature physically possible. At such a low temperature, the radiation is extremely weak, and it exists in the microwave region of the electromagnetic spectrum, invisible to human eyes. To detect it, scientists must build instruments of extraordinary sensitivity, capable of distinguishing the faintest cosmic signals from the noise of Earth, the atmosphere, and even the instruments themselves. The challenge begins with the fact that Earth is a noisy place, at least from the perspective of microwave radiation. Everything around us emits heat. The ground, the air, buildings, electronics, and even our own bodies give off infrared and microwave radiation. To a sensitive detector, this background noise can easily overwhelm the faint signal of the cosmic microwave background. It is like trying to hear a whisper across a crowded, roaring stadium. To solve this problem, scientists developed specialized telescopes designed to isolate and measure the faintest possible signals. Some of these telescopes are placed in remote locations, far from cities and interference. High dry environments are ideal because water vapor in the atmosphere absorbs and emits microwaves. That is why some of the world's most important CMB observatories are located in the deserts of Chile or on the frozen plateau of Antarctica. In these remote regions, the air is thin and dry, allowing telescopes to observe the sky with minimal interference. But even the best locations on wide alert cannot eliminate atmospheric noise entirely. The most precise measurements of the cosmic microwave background come from space-based observatories. By launching telescopes above Earth's atmosphere, scientists can observe the universe without the distortions caused by air, moisture, and temperature fluctuations. One of the earliest and most important of these missions was the Cosmic Background Explorer, or COBE. Launched by NASA in 1989, COBE was designed to measure the spectrum and temperature of the cosmic microwave background with unprecedented precision. Before COBE, scientists knew the CMB existed, but they did not have a clear picture of its structure. COBE changed everything. Its instruments detected the tiny temperature fluctuations across the sky, the first direct evidence of the primordial ripples that would later grow into galaxies and clusters. When the results were announced in 1992, the scientific community was stunned. The data confirmed the predictions of the Big Bang Theory with remarkable accuracy. One of the scientists involved in the project famously described the results as looking at the face of God. COBE's discoveries earned its principal investigators, John Mather and George Smoot, the Nobel Prize in Physics in 2006. But as groundbreaking as COBE was, it only scratched the surface. Its maps were relatively coarse, showing large-scale fluctuations, but lacking the fine detail needed to fully understand the universe's structure. To achieve greater precision, scientists launched the Wilkinson Microwave Anisotropy Probe, or WMAP. In 2001, WMAP was positioned at a special location in space known as the Second Lagrange Point, or L2. This point lies about 1.5 million kilometers from Earth. In a region where the gravitational forces of the Earth and the Sun balance out, from this stable vantage point, WMAP could observe the entire sky with minimal interference. Over the course of 9 years, WMAP produced a detailed, high-resolution map of the cosmic microwave background. The map looked like a colorful patchwork of hot and cold spots, each representing tiny variations in temperature. But behind this simple image lay an enormous amount of information. By analyzing WMAP's data, scientists were able to determine the age of the universe with extraordinary precision, about 13.8 billion years. They measured the rate at which the universe is expanding. They confirmed that the universe is geometrically flat. And they refined estimates of the proportions of ordinary matter, and dark energy. WMAP's single quotes, "A success marked a turning point in cosmology." For the first time, scientists had a detailed, precise picture of the universe's infancy. But even WMAP's measurements were not the final word. In 2009, the European Space Agency launched an even more advanced mission, the Planck satellite. Named after the German physicist Max Planck, a pioneer of quantum theory, this spacecraft was designed to map the cosmic microwave background with the highest resolution and sensitivity ever achieved. Planck carried detectors cooled to temperatures close to absolute zero. In fact, parts of the satellite were cooled to just 1/10 of a degree above absolute zero, making it one of the coldest objects ever created by humans. This extreme cooling was necessary because the detectors themselves could emit heat, which would interfere with the faint cosmic signal. By cooling the instruments to such low temperatures, scientists minimized this interference and allowed Planck to measure the CMB with extraordinary accuracy. when Planck released its first sky map of the cosmic microwave background. The results were breathtaking. The map showed an intricate pattern of tiny temperature variations across the entire sky. It was the most detailed baby picture of the universe ever created, from Planck's data. Scientists refined their measurements even further. They confirmed the universe's age too within a few million years. They measured the proportions of cosmic ingredients with unprecedented precision. They also found subtle, anomalous small irregularities in the CMB that did not quite match the simplest models of the universe. These anomalies remain the subject of ongoing research. Some scientists believe they may be statistical flukes. Others suggest they could hint at new physics, perhaps evidence of exotic processes in the early universe, or even clues about what came before the Big Bang. But space missions like COBE, WAP, and Planck are only part of the story. Ground-based observatories continue to play a crucial role in studying the cosmic microwave background. These telescopes often focus on specific aspects of the CMB, such as its polarization. Polarization refers to the orientation of light waves. Under certain conditions, the cosmic microwave background becomes slightly polarized due to interactions with matter in the early universe. By measuring this polarization, scientists can learn even more about cosmic inflation and the distribution of matter in the early cosmos. Detecting this polarization is incredibly challenging. The signals are even fainter than the temperature fluctuations in the CMB, yet experiments around the world from Antarctica to the high mountains of Chile are working to detect these subtle patterns. If scientists can measure a particular type of polarization known as B modes, it could provide direct evidence of gravitational waves generated during cosmic inflation. These would be ripples in the fabric of space-time itself, created in the first fraction of a second after the universe began. Such a discovery would be revolutionary. It would offer direct proof of inflation and provide a glimpse into physics at energies far beyond anything we can produce in particle accelerators. All of these efforts, space missions, ground-based telescopes, and advanced detectors are part of a single goal: to listen more carefully to the universe's oldest light. Each improvement in technology allows scientists to extract more information from the cosmic microwave background, revealing new details about the universe's origin and evolution. In a sense, these telescopes are like time machines. They do not travel through time, but they allow us to see the past. The light they detect has been traveling for nearly 13.8 billion years. When we observe it, we are looking back to a time when the universe was just a few 100,000 years old. It is a remarkable thought. Every time a CMB detector registers a photon, it is capturing a particle of light that began its journey before the Earth existed, before the sun was born, before even the first stars ignited. These ancient photons have crossed the entire observable universe to reach us. They carry with them the memory of a time when everything was hot, dense, and glowing. And through the careful work of scientists and engineers, we have learned how to listen to their story. By the time scientists had mapped the cosmic microwave background with high precision, a startling realization began to take shape. The universe, it turned out, was not made mostly of the familiar matter that forms stars, planets, and people. Instead, the CMB revealed a cosmos dominated by invisible forces and substances, mysterious components that neither emit nor absorb light, yet control the fate of everything. When researchers carefully analyzed the patterns in the cosmic microwave background, they noticed that the tiny temperature fluctuations followed very specific statistical patterns. These patterns were not random. They were shaped by the balance between gravity, radiation, and matter in the early universe. By comparing the observed fluctuations with theoretical models, scientists could determine exactly how much of each component existed at the time the CMB was released. The results were astonishing. Ordinary matter, the atoms that make up everything we can see, counted for only about 5% of the total energy content of the universe. That meant that 95% of the cosmos was made of something else entirely. About 27% of the universe consists of dark matter. This mysterious substance does not interact with light, making it completely invisible to telescopes. It does not glow, reflect, or absorb radiation, yet its presence is unmistakable. Dark matter exerts gravity, and its gravitational pull shapes the motion of galaxies and the structure of the cosmos. Long before the cosmic microwave background was mapped in detail, astronomers had noticed strange behavior in galaxies. Stars near the outer edges of galaxies were orbiting much faster than expected. According to the laws of gravity, those stars should have flown off into intergalactic space, yet they remained bound to their galaxies, as if an invisible mass were holding them in place. This invisible mass was dubbed dark matter. It seemed to form vast halos around galaxies, providing the extra gravitational pull needed to keep stars in their orbits. But dark matter was more than just a galactic glue. The cosmic microwave background revealed that it played a crucial role even earlier in cosmic history. In the early universe, before the formation of stars and galaxies, dark matter began to clump together under its own gravity. Unlike ordinary matter, which was tightly coupled to radiation and constantly interacting with photons, dark matter did not collide with light. It was free to move and gather into dense regions. These dark matter clumps acted like gravitational wells. When ordinary matter, eventually cooled and separated from radiation, fell into these wells, forming the first structures in the universe. In this way, dark matter provided the scaffolding for cosmic structure. Without it, galaxies might never have formed at all. Yet dark matter, mysterious as it is not the most dominant component of the universe. The cosmic microwave background revealed something even stranger, something that makes up nearly 68% of the cosmos. This component is known as dark energy. Dark energy is perhaps the greatest mystery in modern physics. Unlike dark matter, which pulls things together through gravity, dark energy appears to do the opposite. It pushes space apart. It is responsible for the accelerating expansion of the universe. For much of the 20th century, scientists assumed that the expansion of the universe, which began with the Big Bang, must be slowing down. Gravity, after all, pulls matter together. The combined gravitational attraction of all the galaxies should gradually slow the expansion over time. But in the late 1990s, astronomers studying distant supernova made a shocking discovery. Instead of slowing down, the universe's expansion was speeding up. Galaxies were drifting away from each other faster and faster as time passed. Something was pushing them apart. Something powerful enough to overcome gravity on cosmic scales. The only explanation that fit the observations was the existence of a new form of energy. It's permeating space itself. This energy, dark energy, appears to be an intrinsic property of space. As space expands, more dark energy comes into existence, driving even faster expansion. It is a self-reinforcing process. The cosmic microwave background provided crucial evidence for dark energy's existence. The precise patterns in the CMB showed that the universe is geometrically flat. But when scientists added up all the matter, both ordinary and dark, it only accounted for about 1/3 of the energy needed to make the universe flat. The remaining 2/3 had to be something else. That missing component matched perfectly with the dark energy discovered through supernova observations. Together, the CMB and supernova data painted a consistent picture. A universe dominated by dark energy, shaped by dark matter, and made visible only by a small fraction of ordinary matter. This realization changed our understanding of the cosmos completely. The stars, planets, and galaxies we see are just the tip of the cosmic iceberg. The vast majority of the universe is made of substances we cannot see, detect directly, or fully understand. The cosmic microwave background also offers clues about the ultimate fate of the universe, because it reveals the proportions of matter and dark energy. It helps scientists predict how the cosmos will evolve over billions of years. If the universe were dominated by matter alone, gravity might eventually slow the expansion and pull everything back together in a catastrophic collapse known as the Big Crunch. But the presence of dark energy changes that picture dramatically. Dark energy causes the expansion of the universe to accelerate. Over time, galaxies will drift farther and farther apart. Distant galaxies will eventually move beyond our observable horizon, disappearing from view entirely. The night sky, once filled with countless galaxies, will grow darker as the universe expands. In the far future, trillions of years from now, only the stars within our own galaxy may remain visible. Everything else will have receded beyond the cosmic horizon. Carried away by the relentless expansion of space, the universe, once a hot, dense, glowing plasma, may ultimately become a cold, dark, and empty place. Stars will burn out. Galaxies will fade. Even black holes will slowly evaporate over unimaginable spans of time. This scenario is known as the heat death of the universe's state, in which all energy is evenly distributed, and no meaningful processes can occur. And yet, all of this our understanding of dark matter, dark energy, and the universe's fate comes from studying the faint glow of the cosmic microwave background. It is astonishing to think that by observing light released just 380,000 years after the Big Bang, scientists can predict events trillions of years into the future. The CMB is more than a relic of the past. It is a guidebook to the universe's destiny. But even with all we have learned, the CMB continues to raise new questions. What exactly is dark matter? What is dark energy? Why do they exist in the proportions we observe? And what happened in the very first instant of time, before the cosmic microwave background was ever released? The answers to these questions may still be hidden in the ancient light that fills the universe. Every improvement in our measurements brings us closer to understanding the deepest mysteries of existence. The cosmic microwave background is not just a whisper from the past. It is a message written across the entire sky, waiting for us to decode its meaning, and we are only beginning to understand what it has to say. For all the precision and clarity the cosmic microwave background has given us, it has also revealed something unexpected. Hidden within its delicate patterns are subtle irregularities, features that do not quite fit our simplest models of the universe. These anomalies are small, and scientists still debate their significance. But they hint at the possibility that the early cosmos may have been more complex or stranger than we currently understand. When the Planck satellite released its high-resolution maps of the cosmic microwave background, cosmologists eagerly examined every detail. The overall structure matched the predictions of the Big Bang model with astonishing accuracy. The fluctuations had the right size, the right distribution, and the right statistical properties to support the theory of cosmic inflation and the standard model of cosmology. But beneath this overall agreement, certain patterns stood out. One of the most intriguing features was an unusually large cold region in the southern sky, often referred to as the cold spot. This area appeared slightly cooler than the surrounding regions of the cosmic microwave background, far more than expected from normal statistical variations. It was not dramatically different tonally, a tiny fraction of a degree cooler, but in the precise language of cosmology. The difference was significant enough to raise questions at first. Scientists considered the possibility that the cold spot was simply a statistical fluke. After all, if you examine enough random patterns, unusual features are bound to appear somewhere. But as more precise data came in, the cold spot remained. It was still there, stubbornly colder than its surroundings. Some researchers proposed that the cold spot might be caused by a massive void in the distribution of galaxies between us and the CMB. If a photon of the cosmic microwave background passed through a region of space with very little matter, it might lose a small amount of energy due to the expansion of the universe. This effect, known as the integrated Sachs-Wolf effect, could create a slightly colder region in the CMB. Map. Astronomers searched the area corresponding to the cold spot and did find evidence of a large cosmic void, a vast region of space, containing far fewer galaxies than average. But the void did not seem large enough to fully explain the temperature difference observed in the CMB. The mystery remained. Other scientists proposed more exotic explanations. Some suggested that the cold spot might be evidence of a collision between our universe and another universe in a hypothetical multiverse. In certain inflationary models, our universe is just one bubble among many, each with its own physical properties. If two such bubbles collided in the early universe, The impact might leave a faint imprint in the cosmic microwave background. This idea is highly speculative, and there is no direct evidence to support it. But the possibility captures the imagination. It suggests that the CMB might contain traces not only of our own universe's birth, but of interactions with entirely separate universes. The cold spot is not the only anomaly in the cosmic microwave background. Another puzzling feature is known as the axis of evil, a name given half-jokingly by cosmologists. When scientists analyzed the large-scale fluctuations in the CMB, they noticed that certain patterns seemed oddly aligned along a particular direction in the sky, in a perfectly random universe. These patterns should have no preferred direction. The fluctuations should be statistically isotropic, meaning they look the same in every direction. But the observed alignment suggested a subtle asymmetry. Some researchers believe this alignment may simply be the result of statistical chance. Others argue it could indicate new physics, perhaps a slight rotation of the universe, or an unknown process in the early cosmos that introduced a preferred direction. There is also evidence that one half of the universe appears slightly different from the other. This phenomenon, known as hemispherical asymmetry, suggests that temperature fluctuations on one side of the sky are slightly stronger than those on the opposite side. Again, the difference is extremely small, but in the precise world of cosmological measurements, even tiny deviations can be significant. Together, these anomalies challenge the idea that the universe is perfectly uniform and symmetrical on the largest scales. They do not overturn the Big Bang theory or the standard cosmological model, but they raise intriguing questions about whether our current understanding is complete. Another mystery lies in the very nature of cosmic inflation itself. The CMB provides strong evidence that inflation occurred, but it does not reveal exactly how or why it happened. There are dozens of competing models of inflation, each with slightly different predictions about the early universe. Some models suggest that inflation was driven by a single field, kind of cosmic energy that filled space. Others propose more complex scenarios involving multiple fields or exotic particles. The exact mechanism behind inflation remains unknown. Scientists hope that by studying the cosmic microwave background in even greater detail, they may find subtle clues that distinguish between these models. In particular, they are searching for the faint signature of primordial gravitational waves ripples in space-time generated during inflation. If detected, these waves could reveal the energy scale of inflation and shed light on the physics of the universe's first instant. There is also the question of what came before inflation, or even before the Big Bang itself. The cosmic microwave background only shows us the universe as it was. 380,000 years after the Big Bang, anything earlier is hidden behind a kind of cosmic curtain. Before that time, the universe was opaque. Light could not travel freely, so we have no direct electromagnetic evidence of those earliest moments. The CMB is, in a sense, the furthest back we can see using light, but scientists are exploring new ways to probe even earlier times. Gravitational waves, for example, could carry information from the universe's first fraction of a second. Unlike light, gravitational waves can travel through dense, opaque conditions without being scattered. If we can detect primordial gravitational waves, we might be able to look beyond the cosmic microwave background, peering into the very birth of space-time itself. Despite these mysteries, it is important to remember that the anomalies in the CMB are subtle. The standard cosmological model still explains the vast majority of observations with remarkable accuracy. The universe, as revealed by the cosmic microwave background, is still largely uniform, flat, and consistent with the predictions of the Big Bang theory, yet science advances by investigating the small discrepancies, the tiny cracks in our understanding. The anomalies in the CMB are like faint whispers of something deeper, something not yet fully understood. They remind us that the universe is not just a solved puzzle. It is an ongoing mystery. Every time we look more closely, we discover new questions waiting to be answered. The cosmic microwave background, once thought to be a simple afterglow, has become a cosmic treasure map. It guides us toward deeper truths about the origin of the universe, the nature of reality, and the forces that shaped everything we see. And perhaps, hidden in its faint patterns, are clues to questions we have not even thought to ask. Even after decades of study, the cosmic microwave background has not given up all of its secrets. The maps from COBE, WMAP, and Planck have transformed cosmology from a largely theoretical science into one of the most precise fields in all of physics. Yet the questions that remain are among the deepest ever asked. What exactly is dark matter? What is the nature of dark energy? How did cosmic inflation begin? And what came before it? To answer these questions, scientists are preparing the next generation of experiments designed to listen to the universe's oldest light with unprecedented sensitivity. The next frontier. And CMB research focuses on something far more subtle than temperature fluctuations. It focuses on polarization, tiny directional patterns in the cosmic microwave background that may carry the fingerprints of the universe's earliest moments. While temperature variations show where matter was slightly more or less dense, polarization patterns could reveal the influence of gravitational waves from the dawn of time. In the first fraction of a second after the Big Bang, during the era of cosmic inflation, the universe may have experienced violent ripples in space-time itself. These ripples, known as primordial gravitational waves, would have stretched and squeezed space as they traveled. As the universe cooled and the cosmic microwave background formed, these gravitational waves would have left behind a faint but distinct pattern in the polarization of the radiation. This pattern is known as B-mode polarization. It is incredibly faint, far more subtle than the temperature variations already mapped by Planck. Detecting it requires instruments of extraordinary precision, capable of distinguishing signals a billion times weaker than everyday sources of microwave radiation around the world. Scientists are building and deploying these instruments. In the frozen isolation of Antarctica, telescopes stand on the vast, silent plateau of the South Pole, where the air is thin, dry, and almost completely free of atmospheric interference. These conditions make it one of the best places on Earth to observe the cosmic microwave background. Meanwhile, high in the Atacama Desert of northern Chile, another set of telescopes scans the sky from altitudes above 5,000 meters. The air there is so dry that some regions receive less rainfall in a year than many places receive in a single day. From these extreme locations, researchers are searching for the faint polarization patterns hidden in the CMB. One of the most ambitious upcoming projects is the Simons Observatory, a collection of telescopes designed specifically to study the cosmic microwave background in exquisite detail. Equipped with thousands of sensitive detectors, the observatory will measure both temperature and polarization across large portions of the sky. Another major project on the horizon is CMBS-4, a next-generation ground-based experiment that will combine dozens of telescopes across multiple sites. With hundreds of thousands of detectors, CMBS-4 aims to create the most precise measurements of the cosmic microwave background ever achieved from Earth. These instruments will not only search for primordial gravitational waves, they will also map the distribution of matter across the universe by observing how the CMB is distorted as it passes through massive structures like galaxy clusters. This effect, known as gravitational lensing, slightly bends the path of the CMB's photons. By measuring these distortions, scientists can create detailed maps of dark matter across the cosmos. In addition to ground-based experiments, new space missions are also being planned. Space offers the ultimate observing platform free from atmospheric interference, temperature fluctuations, and radio noise. A new generation of satellites could measure the cosmic microwave background with even greater precision than Planck. These missions may be able to detect signals that are currently beyond our reach, subtle features that could reveal new physics, unknown particles, or even evidence of phenomena that occurred before inflation. As technology improves, scientists are also exploring entirely new methods of observation. Some researchers are developing ultra-sensitive detectors cooled to temperatures just a fraction of a degree above absolute zero. Others are experimenting with quantum technologies that could push the limits of measurement even further. The goal is simple but profound: to extract every possible piece of information from the cosmic microwave background. Every photon of the CMB carries a tiny fragment of the universe's history. By studying these photons in greater detail, scientists hope to reconstruct the story of the cosmos with unprecedented clarity. But the significance of these efforts goes beyond pure science. The cosmic microwave background is more than just a research topic. It is a reminder of our place in the universe. The light we detect from the CMB began its journey long before Earth existed. It traveled across the expanding cosmos for billions of years, passing through regions where galaxies would later form, drifting past stars that would one day burn out, and crossing distances so vast they are difficult to comprehend. And now, after nearly 13.8 billion years, a tiny fraction of that ancient light reaches our detectors. It carries with it a message from the dawn of time, a message about the birth of the universe, the formation of structure, and the forces that shaped everything we see today. In a sense, every observation of the cosmic microwave background is a conversation with the past. It is a way of listening to the universe's earliest memories, preserved in the faint glow that fills all of space. As we build more sensitive instruments and develop more advanced theories, we come closer to answering some of the biggest questions ever asked. What is the universe made of? How did it begin? And what is its ultimate fate? The cosmic microwave background may hold the answers. Hidden within its delicate patterns could be clues about the fundamental laws of physics, the nature of space-time, and the origins of the cosmos itself. The journey is far from over. In fact, we may only be at the beginning. Each new experiment, each new map of the CMB, brings us closer to understanding the story. It's written in the universe's oldest light. And as we continue to listen to this ancient echo, we may discover that the universe still has many secrets left to tell.